We've introduced the null space of a matrix A, and we talked about how to find it from the echelon form U of a matrix A. We're going to introduce a new form now called the reduced row echelon form, and you will often find it with this notation, especially if you use software such as MATLAB or maybe even Python, where if you want to find the reduced row echelon form of a matrix, you just literally type RREF of A and it would produce that R. Anyway, this notation is not key here. Question is, what is the reduced row echelon form of a matrix? And the best way to see it is on an example. So in the previous video, we had the matrix A. At the end, we had the matrix A to be 1, 2, 2, 4, 3, 8, 6, 16. We applied elimination, and we got to the matrix U. So this over here is U. Now from U, we can do a little bit more to get to the reduced row echelon form R. What is the reduced row echelon form? Well, the goal is to have the pivot value equal to 1. So the first pivot is already a 1, no problem. So we need to continue to carry out these elimination steps or elimination operations that we know of to get a 1 in each pivot position, and then eliminate not only below but also above the pivot. So I'm going to want to eliminate above the pivot as well. The first step to creating, the first step will be to get a 1 instead of the 2. So that operation is simply R2, 1/2 R2 into R2. So I can divide the second row by 2 everywhere. That's an allowed operation. I'm going to get 1, 2, 2, 4, 0, 1, 0, 2. It's nice to work with smaller numbers, so this is a nice change. And then I'm going to use that pivot column and eliminate above, just like what we do in the Gauss-Jordan method. The operation in question is R1 minus 2R2 into R1, and the result is 1, 0, 2, 0, 0, 1, 0, 2. So this form is what we refer to as the reduced row echelon form of A. The pivot columns come from the identity matrix. So you have one pivot column and another pivot column. The columns of the identity matrix have a 1 in one location and zeros everywhere else. In this case, a 1 and a 0. And so these over here are the free columns. Now, let me just write that. These two columns are pivot columns. You see the pivots are both equal to 1, whereas these two columns are free columns. Now, it is much easier to find the special solutions or to calculate the special solutions when you're looking at the reduced row echelon form of A. So just like we started with the system AX equals 0. We got to the system UX equals 0, and we continued then with elementary row operations and got to RX equals 0. All of these systems have the same solutions. The null space of A is the null space of U is the null space of R. So one could choose really any of these matrices to find the null space, but it is easiest to do that in the reduced row echelon form. Each free column gives you exactly one special solution, and then all linear combinations of the special solutions give you the null space. So if you recall, when we looked for special solutions, we would set one free column or free variable to 1 and the other one to 0. So if we set x3 to 0 and x4 to 1, for example, you see x4 no longer has a non-zero coefficient in the first row, so the first row is not going to give us anything beyond, well, I guess it's going to give us x1, it must also be 0. But anyway, from the second equation, we have x2 plus 2x4 is 0. Since x4 is a 1, we see that x2 from here must be a negative 2. And then from the first equation, we have x1 plus 2x3 is 0. x3 is already 0, so x1 must also be 0. And this is exactly the solution that we got, the one special solution that we got when we were working with u. So we have x1 is 0, x2 is a negative 2, x3 is 0, x4 is 1. And in fact, you see, you still have the 2 and the 1, and if you just look at maybe what's the easiest vector orthogonal to that one, and you get x, you get this special solution. The other special solution is when we set x3 to be 1, but x4 to be 0. There we get from the second equation x2 plus 2x4 is 0. Since x4 is 0, it follows that x2 must be 0. And then from the first equation, we have x1 plus 2x3 is 0. Since x3 is 1, it follows that x1 is a negative 2. And so this special solution, the second one, is negative 2, 0, 1, 0. So nothing new here. We got the same solution as when we were working with u, but it is much easier to see it. In fact, I personally will just look at the two vectors here, the two rows, and if I'm trying to find, I guess what is important to note is that because we want this row dot product with that column to be 0, in fact, these column vectors that we are looking for in the null space are orthogonal to each row of A or R or U. So I'm just looking for two linearly independent vectors that are going to be orthogonal to both rows. So if I find something that has non-zero terms here and 0 terms there, because these two rows are in fact orthogonal to each other, then I know I will find another vector which is orthogonal to both. So by putting a 1 here, I see immediately I need a negative 2 there, and I can do that same trick with the second row. I can put a 1 here and a negative 2 there, and I will get that orthogonality, and the vectors will again be linearly independent, because if I have non-zero here, but then 0 over here, that would be linearly independent with a vector that would have non-zeros the way this one has non-zeros. So those are the advantages of the reduced row echelon form. It's actually quite easy to see that the third column is 2 times the first column. Even in U, that is true. The third column is 2 times the first. And in A, that's also true. The third column is 2 times the first. Then we see the fourth column is 2 times the second. And indeed, the fourth column is 2 times the second. The fourth column is 2 times the second. So the relationship between the columns is the same in all of these matrices, including this intermediate one. Before we close off, let's look at one more example on a bigger matrix, started from scratch, trying to use the reduced row echelon form to find the null space of the matrix. So let's take the matrix A with columns 1, 1, 1, 1, 2, 3, 2, 2, 2, 4, 5, 6. We will get first to the reduced row echelon form of the matrix and then find the null space of A. So we start with the first pivot, eliminate underneath it. We have R2 minus R1 into R2, R3 minus R1 into R3. We get 1, 1, 2, 4. Then 0, 1, 0, 1, then 0, 2, 0, 2. Here is the second pivot. We eliminate underneath it. The operation is, in fact, we could do something dual because it's already 1. We could eliminate underneath and above at the same time. So we would have R1 minus R2 into R1, and we would have R3 minus 2R2 into R3. And this is allowed because we are changing something, or we are carrying out elimination in the first row using the second, and in the third using the second. But the point is that the second row stays the same, so these operations are independent of each other. The result will be 1, 0, 2, 3, 0, 1, 0, 1, and then 0, 0, 0, 0. Now this is the reduced row echelon form of the matrix A because the pivot columns have a 1 in the pivot position and 0 everywhere else. So the two columns come from the identity matrix. It is quite easy to see how the free columns, so these obviously are the pivot columns, and these over here are the free columns. For each free column, we get a special solution that goes into the null space of the matrix. The matrix is 3 by 4, which means that the solutions to AX equal 0, the x's will have 4 components, and therefore the null space is a subspace of R4. And now let's find that null space. So to find those special solutions, let's set x3 to be 1 and x4 to be 0. It really doesn't matter whether you do first x3 is 1 or x4. It's all the same. So from the second equation, we will have x2 plus x4 is 0. Since x4 is 0, it follows that x2 is also 0. From the first equation, we have x1 plus 2x3 plus 3x4 is 0. x4 is 0, so that doesn't play a role. Whereas x3 is 1, so you have x1 plus 2 is 0, which means that x1 is a negative 2. And so the special solution is negative 2, 0, 1, 0. And kind of obvious that this truly is orthogonal to the first row and to the second row. The second special solution is we get it by setting x3 to 0 and x4 to 1. So from the second equation, we get x2 plus x4 is 0, which means that x2 will have to be a negative 1. And then from the first equation, we have x1 plus 2x3 plus 3x4 is 0. x4 we know to be a 1. x3 is 0. So we have x1 plus 3 is 0, which means x1 is a negative 3. And so the other special solution is negative 3, negative 1, 0, 1. You can quickly check to see that these two x's are orthogonal to both rows of R, which will imply that they're also orthogonal to all rows in A. You can certainly check that that is the case. So from here, the null space of A is the span of the special solutions Note that the special solutions are always going to be linearly independent, and that is important to us. I don't want to give two vectors that are multiples of each other. That doesn't give me new information. But these two vectors being linearly independent and describing the entire null space, they tell me that the null space of A is a plane in R4. So this is a plane in R4. Why R4? Because the vectors have 4 components. Remember when we talked about the column space of A would consist of the columns of A. And in fact, to describe the column space, we only look at the pivot columns. Now, the column space of A and the column space of R are not the same. Observe that if you combine the columns of R, the third component will always be 0, no matter how you combine the columns. In fact, it is enough to look at the pivot columns. And you see that the column space of R will contain any vector with 3 components, which has the third component equal to 0. So any vector that has the third component equal to 0 will be in the column space of R. But that is not the same as the column space of A, because in the column space of A, the third component could very well be non-zero. The interesting thing is that if the column space of R is described by 2 columns, which are linearly independent, and they're the pivot columns, those corresponding columns of A describe the column space of A. So just a reminder, I'll write it over here. The column space of A is span of the pivot columns, which in our case are 1, 1, 1, and 1, 2, 3. So you see, the column space of A is a subspace of R3. Because the columns of A have 3 components, whereas the null space is a subspace of R4 because there are 4 columns. So if you count how many vectors you need to describe the column space of A and how many columns you need to describe the null space of A, they will always add up to the number of columns of A, even though these spaces actually are subspaces in different spaces. So one is a subspace of R3, the other one is a subspace of R4. Only in the case of square matrices, both of those will be subspaces in the same Rn space. The number of pivot columns of a matrix, we've already noted that, is called the rank. So rank of a matrix A, sometimes denoted like this, equals the number of pivot columns of A. And there is something called nullity. That is the number of free columns. of A, which is the same, which is equal to the number of special solutions to AX equals 0 that help us identify or describe the null space of A. All right, that's all for today.